Okay, we're going to get started with our next section. Will everybody please take a seat? Next will be speaking is Dr. Les Kuhlman, who is an employee with Pioneer. Dr. Kuhlman is originally from Manhattan, Kansas, and earned a Bachelor of Science degree in Agronomy from Kansas State University, and both a Master of Science and Ph.D. in plant breeding from Texas A&M University. Dr. Kuhlman began with DuPont Pioneer in 2007 and started the Lawrence Soybean Research Station in Lawrence, Kansas, which is responsible for product development for the Kansas and western Missouri soybean growing regions. Additionally, he manages a group of scientists that research advanced molecular breeding techniques for use in breeding program. Today, Dr. Kuhlman will be speaking to us about commercial soybean breeding in a changing world. Please help me in welcoming him.
Can you hear me with this? Is this good? Okay. All right. Well, I sure appreciate the invitation and introduction. Well, I can go to here. You did a great job introducing me. I want to say thank you to everybody for inviting me to the symposium. I did graduate from A&M, so this is pretty fun to come back and see colleagues, professors, other students that I went to school with, and then be able to give the students here somewhat of a introduction to your early career. So I've been out of school, it'll be 8 years this summer, and so I can give you a synopsis of what the corporate world has done to me in 8 years, and pros and cons of that. Probably not very many cons, but some pros. So I was born in Manhattan. I'm a K-Stater, so I retained the Go Cats motto the whole time through. But I absolutely cheer for A&M now that I'm away, so that stuck with me. I'm one generation removed from a family farm, so I was that was instilled in me. Wheat farm from western Kansas. Really wanted to be involved in agriculture, but not in a production sense. So went to K-State, came to A&M, and did plant breeding. I was with Dr. Rooney. Did grain sorghum for a master's degree, and then for a Ph.D. did interspecific crosses in sorghum. And then I got the opportunity to join Pioneer in 2007. I actually started a breeding program. So it's one of those things where you graduate with a plant breeding degree and get the opportunity to actually start your own thing. You sort of jump at that. And so I did. Started with no employees in someone's basement. That was the first office. And then grew it into a full breeding program that is what it is today. So I'm going to go through and try and just give you a scope. This presentation, we've had a lot of great presentations today, and mine will contrast in that it's from a specific perspective, the industrial perspective, and sort of what that does. So I'll just get right into it. So the first I wanted to give you a scope of sort of the pace of change, and this is the pace of change from my limited perspective, which is going to be different than others who've been here a lot longer. So the dawn of time for molecular genetics would be the isozyme period pre-90s. First time, right? Bob Klein's already laughing. Dawn of time for me. But there's the first time you could actually take a signal from the plant and relate it to genetics. So instead of just looking at the phenotype, you're actually able to figure out a signal that's coming from the DNA. So that's pre-90s. Pioneer initiates QTL mapping for SCN resistance. SCN is soybean cyst nematode, largest yield-limiting pest of soybeans, below-ground nematode, parasitic. Major sources of resistance. So we started that in 1993. So this is doing RFLPs, very labor-intensive. Mapping population, found major QTLs, and began actually forward breeding with those in 1995. So, 1995. First marker-assisted selection in Pioneer. That is the backbone of marker-assisted selection still today, where we've been able to go from essentially 0% resistance in the products we release to essentially 100% resistance, modulated through one single gene that allows for resistance to the major race that we have. As host plant resistance evolves, though, as does this, today we deal with a couple other sources of resistance to mitigate the changing race populations we've got. So that's in the mid-90s. So fast forward a couple years 2001, the genetic map for soybeans in Pioneer is maybe 350 SSRs. We're big time, right? This is big stuff. I'm starting grad school. SSRs are the big thing, and we're really dense. We got a lot of markers. A couple years later, wow, we can double that. Okay, 800 SSRs in just the span of a couple of years. Another 5 years, all of a sudden, within Pioneer, we've transformed into SNPs, and all of a sudden, we're using an aluminoplex, so 1536. We are big stuff when we start. It takes another couple of years, and we double that again. So we're dealing with Moore's law here, doubling every couple of years. And then what really changes the game is resequencing. So we go from having 3,000 markers to having all the SNPs. Let's just all of them on anything we need. So what does that do? As a breeder, maybe your head just explodes a little bit in that now you don't have to have you can't use the excuse of, well, we don't have enough marker data. Well, you do now, so what's the answer? That's a challenge. But the scope here is within a couple 20 years, we've gone from incredibly basic molecular tools to being able to have all of the genetic data in a population, and now what can we do with that? So the key for an industrial perspective is how do I turn that data, which it's just a bunch of ones and zeros, right? It's nothing other than just data. How do you turn that into information, which then can be used by someone to actually create value, right? So it's not valuable unless it shows up in a product. So either we have more resistance, we have more yield, something changes in that product, so our customers buy it, and that's value, right? If I can't create value out of it, why'd we do it, okay? All right, so I start most presentations with this, soybean genetic gain over time. So I'm a plant breeder. I'm responsible for products in my region as well as a broader region. And this is really where the rubber meets the road, right? So this is on-farm soybean yields from 1924 to 2010, so about 85 years. And we've got a nice progression here, right? So we've got an upward curve, about 1/3 of a bushel per acre per year. So that's going to be genetics and then production practices as well. You can see a couple of things here. We have, in the mid-70s, we seem to have a whole bunch of variability show up in our graph. We had a nice linear upward swing, and then we get a bunch of variability. A couple things going on. Soybean cyst nematode shows up, so you have swings in yields up and down, as well as acreage begins expanding. So in the mid-70s, there wasn't a lot of acreage in Kansas. Well, there is today. Well, when drought hits, Kansas pulls the national average down. So as acres move more marginally, you get bigger swings. So you can ask one question here is, surely we're doing better today than we were 50 years ago, right? So surely the pace of change today is a lot higher than that. The industry invests a lot of money in this. Hopefully we're doing better. And we are. So if you ask a different question, say, are there two different curves on that same data set? The answer is yes, there are. So the first curve is for the first 50 years, 1/3 of a bushel per acre per year. And then in the last 30 years, we've inched that up to about 1/2 a bushel per acre per year. So that's great. That means we're doing better today than we were previously. Why is that? Is it we're just better at our jobs? I hope so, but probably not. So Pioneer didn't sell soybeans in 1970. Okay, so there was a huge industrial investment in soybean breeding in the mid-70s. So Pioneer would have bought Peterson Seed Company in 1974 and started selling seed. And so that was a time of lots of industry investment in soybean breeding, so you get a lot more researchers. So a lot more research in the mid-70s, as well as then marker technologies taking hold in the mid-90s and 2000s. So those marker technologies we made investments in the mid-90s wouldn't actually show up in varieties until the 2000s. So those technology investments are paying off, and we're getting higher returns. So I put these up here not to do anything but point out any technology that we introduce has to show up on this curve somehow, or we really haven't done very much, right? So we talk about whole genome predictions. We talk about a lot of stuff that we do today that's really fancy and really, it sounds awesome and you get all the publications out of it. But if it doesn't change this curve, we haven't done anything for the producers. Okay, so that's sort of how we benchmark what we're doing. Okay, so commercial breeding. What is it we're doing here? We're highly focused on our customers. So these are a couple statements that contrast from, well, I think that differentiate us. So we are highly focused on our customers. Are your breeding targets capturing value? And by value, we mean value. So if I try and sell a bag of seed to someone, is what I'm working on valuable to them? So if I produce, you know, a soybean crop that is, for example, higher oil percentage. Someone asked me about that. Higher oil. Hey, great. Are they going to get paid for that? Because if they're not going to be willing to pay me for that. So it's an incredibly simple, you know, continuum from value to the producer to what I'm working on. So all of my trait targets absolutely have to be relevant to what the farmer is going to get paid for, because that's why they're buying your seed. So your breeding targets may not necessarily be what you'd like them to be. They are what you get paid for. We're a resource to win in a way that if a company is going to have a breeding program in Lawrence, if I'm not successful, then they're not successful. So it's in their best interest to make sure that we're doing what we're doing. So the resources are not a big limiter. We're always looking for that edge, all right, to increase genetic gain. You're always looking for that next thing. Because as we say, if you're not, your competitors are, right? So it's a competitive game. Monsanto's our biggest competitor. If we're not doing it, they are, right? And so you always have that drive to keep doing something new and making yourself better. It's highly collaborative. I think our breeding programs are really focused on delivering products, but yet there's a lot of scientists within a company who work for your same goals. And so it's a very collaborative nature in how to do things. I don't think that's different than public. It's just everyone is focused on that goal, and you work together. So I'm going to give a couple, I think I have 4 examples of technologies we use in the breeding programs, and then I'm trying to pull out for the plant breeding students some of the lessons I've learned over 8 years to apply to you guys. So Dr. You did a great job of going through whole genome predictions this morning, so I'm super glad I didn't spend a lot of time. This is, from a plant breeder's perspective, this is how whole genome prediction works. You've got one group that's your training set, one is your prediction set. You train it and then predict, and that's really all I understand about it, which isn't true. That's why I'll get into this. So I'm going to talk about maturity as my first example, and I had to throw a picture up here. Soybeans are not a highly common crop down here, so I wanted to make sure you guys understood what maturity is. This is a result of a couple extra field resources we had to use, and so these are maturing soybeans in plots. This would be September. All the brown plots are normal maturity, and they're maturing, and then the design is a group 7 variety that's not going to mature ever. Okay, so you get this nice pioneer symbol in the middle of the field. Probably, you know, farmers driving by are pretty happy about this. So that's what we're talking about. Maturity is the time from planting to harvest. All right, so the first example here is whole genome prediction for soybean maturity. So like I said, maturity is time from planting to harvest. We talk about maturity on the x-axis down here, predicted maturity in relative maturity. So you'd go from 00 all the way to group 7 or 8, okay? And so what we have here is whole genome prediction. See, I've got about 190 individuals was in the training set. We applied it to that set. And so what we're showing here is the predicted maturities are the cross-validated predictions. So they're independent from the training set. And then on the y-axis, we have the actual phenotypic maturity, all right? And so, you know, the R squared here is 0.87. So that's really great. You can actually predict maturity, and that's fantastic. So the example where I'm going here is, you know, this is a great result. Everybody looks at this and says, that is excellent. You know, what else do you need? So as a breeder, what do I do with this? Because A, I didn't produce this data, right? So a collaborator did the predictions, handed me the results. They said, look at this fantastic R squared. Why don't you use this in your breeding program? Okay, well, let's take a look. So here's the same prediction, but this is actually when it's applied to my experimental R2s that I've got. and I look at that and say, wow, that's really not that good, right? That's an R squared of like 0.1. Where did we go wrong here? My collaborator looks at this and says, wait, what are you doing? I mean, I produced those results, they were great, until you touched them, now they're terrible. So what this is, if I can show you this, so these are my experimental lines. Notice that, so one thing to notice here is we don't have the whole spectrum. We only go from, about a 3,5 RM, mid group 3, all the way through a late group 4. I don't grow zeros and I don't grow sevens, right? I have a segment in there. And so if I were actually to use these, how would I use them? Well, what I'd do is you'd use the prediction, right? And I want to grow these late group 3s where they're supposed to be grown, which is in the northern testing sites. If I were to do that, I would use the prediction, right, to select those maturities, and I would put them in the right tests, and I'd grow them. Well, what would happen is these individuals would be tested correctly, right? So they're predicted to be late group 3, okay, 3.5 to 4.0, and they turn out to be late group 3, 3.5 to 4.0. That's a win. These are not a win. So these are 4.0 to 4.9. So if I were to do this, I would get a call from my staff members when they show up to my northern sites to harvest, and they would say, I can't harvest this, right? These are ready to go. We're ready to take yield. And then all these other entries that are in the experiment have 10 days to 2 weeks before they're ready. I can't do this, right? Abandon ship. Let's get out of here. Total fail. All right. So what's the problem here? So we had, collaborators said these predictions are fantastic. I take a look at them. They're completely not fantastic. What's going on? So this graph shows both experimental sets together. My experimental lines in red, and then the training set in green. So the problem here is not the predictions. All right. Both prediction sets together. The R squared's fine. Mine aren't really any different. The problems are perspective. Okay. So the perspective is we did predictions from triple group 0 to group 7. Can you predict group 7 from triple 0? Sure can. But can I predict what's really important, which is a 3.6 from a 3.9? No, I cannot. All right. So the predictions are completely fine. It's just when we evaluate them, we need to have the breeding perspective in mind to figure out whether they have value or not. And well, let's see. Yeah. That's my point. Is the value from an R squared standpoint isn't always the value from a breeding standpoint. So some key learnings here. Perspective of a breeder are often very different from scientists conducting the research. Not all of you may run breeding programs when you get out into the world. And so you have to understand when the breeder's in the field doing their work, if you're providing data or you're assisting them, or maybe you are the breeder, there are two different perspectives coming to the table, and you need to be aware of that. Breeders have to be willing and capable to ask really good questions. When you get data from someone else, you have to be able to you have to ask those questions. You have to know. Taking data at face value is not going to cut it. So it really is all about it's communication. So plant breeding lesson number 1. I have 4 of these. Number 1 is understand your data. So we'll see how good Roger Borma has many more years of experience in soybeans than I do. We'll see how his do. But understand your data, right? You cannot be a successful breeder unless you understand your data. Okay, I've got 3 other examples, and these are going to relate to taking quantitative traits and attacking them, okay, in a couple different ways. Not that maturity wasn't quantitative, but in a different way. So this Venn diagram is just a very simple way to think of QTL and context. So each circle represents a population. Sometimes it could be an environment, but let's think of them as a population. So when we map a trait, let's say it's a disease resistance, or it's very qualitative, you're going to find a major additive QTL, right? Soybean cyst nematode resistance, that's what RHG1 is. It's a huge QTL for resistance. It works in every single population. It's really easy, right? Low-hanging fruit, pretty much all of those are knocked out in the major crops. Well, in soybean at least from my perspective. These QTL down here would have been only identified in one population, right? So they did not repeat in these other populations because they didn't show up, in these common areas. We normally interpret these. Well, depends on how you interpret them. You could interpret them as their error. We didn't do it right. Or they could be their context specific, meaning these genes are operating differently in different genetic backgrounds, and those QTL don't perform across populations. But this is what we're going to talk about now. So one example here is we are mapping yield. All right, so this is a bipolar population. We've got probably 400 individuals phenotyped in the field, good quality data on both sides, probably a couple hundred markers here. We've got chromosome number on the bottom, and we find a huge QTL. Very exciting. Log score of 10, something big is going on here. We go and find the same QTL. What these colored bars are that same QTL showing up in a different population. So each colored bar is a population. So what we're seeing here is that QTL is huge, and it's repeating across lots of populations, and it's for yield. Let's throw a party. That's big. So here's what we've got. So again, this is an example of research going on maybe in silos in different areas of the world. The breeder looks at this and says, hey, that's great. There's a maturity gene in the same spot. So that's not a yield QTL, that's a maturity gene. Good job mapping maturity, though. We need that. Yield and maturity in most crops, many crops, are strongly correlated. So you have a regression when you're a later maturity soybean, you have higher yield. And so in all these populations, when you are later maturity, you're higher yield, and it's a very big effect. Soybeans are photoperiod sensitive, and so we have about 8 photoperiod genes that drive maturity. And when you have one segregating a population, it has very large effects. And so what we've done is just mapped maturity, not yield. Plant breeding lesson number 2, scientific skepticism pays dividends. I don't mean to bring up these examples as well, I like to bring up negative examples. I think it helps steer the ship. But what this shows is, if you're a breeder, this would be intuitive to you. You would map this and say, wow, there's something here, but I know what it is. It's E2. If you're not a breeder, the lesson here is learning all those things that are important to breeders. That's absolutely critical to your job, right? So if your goal is to help breeders or help a company, advance yield in corn or soybean, you have to be just as knowledgeable as the breeder is about the genetic components that go into yield or any other trait as the breeder is. It helps you do your job too. All right, quantitative trait number 2. This example is very generalized here for an important soybean fungal trait. We've got 2 significant medium effect QTL identified in some mapping populations. 2 different medium effect QTL identified in a different population. The heritability, the phenotype of this trait is high. Okay, so if you were a student in this class and a professor gave you this problem, what are you going to do? So you've got QTL being identified. They seem to be context specific because they're not repeating, but the heritability is high. Something's not right here. What's going on? Oh, sorry. Whole genome prediction has shown low predictive power. Okay, so it seems like there's 2 things going on that aren't matching. Usually when you have high heritability, you have whole genome predictions are great. What's going on? Okay. Right. So what we've got here is we took a panel of lines and phenotyped them. This trait is hard to phenotype for, but we made the effort and did this, and we found these parents. So what we have is the columns are parents, okay, and then they're classified as either resistant or susceptible, and then and then we have, this is high density data. So this is essentially the resequenced genome and all the SNPs. So this panel would be looking at the whole 4.5 million SNPs. And so each of these small lines, these small colors like this one and this one is about 10 kb. And within those 10 kb is probably 50 SNPs that form that haplotype. So what we did was each of these haplotypes is 90% similar. And so you're able to say that the haplotype within those 50 SNPs is 90% similar, so you're calling different colors. But what you see here are patterns emerge. Okay, so our resistant here all share this red haplotype, and all our susceptible have this blue haplotype. And so the patterns actually match our genetic understanding. So this is actually telling us what we thought we knew, was that these resistant ones have the same haplotype and these susceptible do not. What's interesting is those patterns are not present in the low density data, right? So when we have 3,000 SNPs, which means you have a SNP there and one there and one there, the patterns are not there, and so you don't have enough power to actually find these. Lesson number 3 is know the basics. This is bulk segment analysis, essentially, right? You have a panel of resistant and a panel of susceptibles. When I was in grad school, we talked about this a lot, but we struggled with it because when you only put a couple hundred markers or 3,000 markers on it, you don't find anything. You don't find the SNPs that are informative and that are in 100% LD with your trait, right? That's the problem is your SNPs aren't in linkage disequilibrium with your actual QTL. If you have a SNP that's not in LD, it doesn't look any different when you do bulk segment analysis. So is this a new concept? Not at all. This is incredibly simple. It's just when you use it with all the data or enough data, the correct patterns which you thought should emerge do emerge. And that's really powerful and very empowering as a scientist to say, I've struggled for so long with this trait, turns out I just needed more data and the right stuff shows up. So know the basics. Example number 3. So let's talk about yield. We have not talked about yield very much today. That's what we get paid for, so that's what we have to figure out. So the situation for yield is large effect QTL don't show up. There's lots and lots and lots of small effect QTL that show up in specific populations, but rarely repeat. Whole genome prediction efficacy for yield within elite breeding populations is low. Okay, so it's low. Doctor, you did say it's higher than 0, which is incredibly important because if you can implement whole genome prediction where you don't have selection, anything better than 0 is a win. But that's not enough. All right, so yield QTL are context specific. How do we take that paradigm and apply it to breeding? Okay, so yield is our most important trait. It is what we get paid for. This is the toughest nut to crack. How do we do it? So what I'm going to describe in soybeans is how we do it. It's called AYT, context-specific mapping. So we take that paradigm that all yield QTL are context-specific, take it to heart, and let's leverage it, and let's just go. So each biparental population is genotyped and phenotyped. The estimation set is the prediction set. It's all the same. You don't have two different things. What that means is the populations have to be large enough to actually estimate genetic effects. So we're talking thousands. No efforts made to apply predictions from one family to a different family. So if I have 50 families, I have 50 predictions. If I have 600 families, you have 600 predictions. You're not trying to apply anything outside of its context. The results of that is predicted yield is better than the phenotype. So when you get past the paradigm of what's our threshold, right? What is our bar? What's the bar we're trying to clear? If we're trying to clear 0, we can do that. If we're trying to clear a combine, it's higher, right? But you can do it using this. I should put more pictures in here, but this is our combine. These are going to be soybean plots. This is first generation plots. So if you're a corn breeder, this is like a DH, right? A very small row. Soybeans, this is a plant row. So one of these rows is derived from a single plant. These are going to be F3 derived F4 plant rows. A breeding program would have 30 to 50,000 of these. A combine is going to harvest 2 of them, split down the middle. And so what you have here with AYT is each of these rows is one SIB of that family, right? And so what we're doing is we're genotyping each one of these individuals and phenotyping them. So then the genetic model we create, we apply back onto those same individuals, and you select using the genotype as opposed to the phenotype. So once the combine's gone through and you create the prediction, you never use the combine data, you use the predicted data and move on. Let's see, lesson number 4, be science driven. This example is really important internally to our company because this is a breeder driven concept. So this technology basically came out of the problem of we have whole genome prediction but it doesn't work for yield, and the breeders want it to work for yield. How do we make it work for yield? And this is what it is. All of these decisions, all the parameters which I didn't go into, and all of the actual results which I didn't show, are all breeder driven, but it's science-based. So how many individuals should be in the population? Do the science and figure it out. How many markers should you have in each genotype? Do the science and figure it out. All those questions aren't necessarily left up to other people, right? Own it and do it. Okay, so the Holy Grail. So you've got breeders. Okay, so they are immersed in breeding, field plots, walking plots, releasing varieties. They are not so great at having time to do whole genome predictions, researching statistical genetics, doing any of that. All right, during harvest they're nowhere to be found, and they don't answer email. There's another group of people, statistical genetics. We call them breeding technologies. We call them, whatever. But they are highly skilled in the sciences of statistics, predictions, doing all those things. But usually they don't have to walk field plots. They don't have those responsibilities. Very important. Third group, genomics. They have access to wet labs. They can run whatever markers you need. They can do your whole genome resequencing and tell you what the data actually means. The Holy Grail is when those three things actually communicate and work together. When that triangle operates, really great things happen. Because each of these groups is important in the science, and when one of them breaks down, you're missing a big piece. So, from my vantage point within the corporate world, getting that triangle to work is really, really important and has been successful. That last statement is probably the one that took me the longest to figure out. Maybe it took me 5 years into my career to figure that out. You'd graduate and you'd say it. You'd say, yeah, it's all about the people. It's all about the people. But you didn't really mean it. And then halfway through the career, you realize, actually, it is all about the people. I should treat it that way. The people on your team, your staff, that's how it actually works. And so the quicker you understand that lesson, the better it's going to be. So it's all about the basics. Understand your data, be skeptical, apply the basics, and be science-driven. What's the most important lesson I learned here? I learned a lot of lessons at Texas A&M, but the one that really resonates with me the most, that I think I could look back on and pinpoint, was from Norman Borlaug. He was alive when I was here, and he would come to our plant breeding circles and talk. And he said, paraphrasing because I don't remember exactly what he said, but at one of them we asked him what was the most important thing that he took from his study or from life. And he essentially said, if you want to see the change you want, you have to see the process through from beginning to end. And what he was referring to was if he would have just created dwarf wheat, but not, made sure it was imported into Pakistan, he wouldn't have made as big of an impact. So if you would have just traded off, just handed off his product and not seen it through to the end, he wouldn't have created that change. And I take this from the, my internal perspective in corporate America as if you want that science to happen from beginning to end, you have to be a part of it. And as a breeder, you have to be present and you have to be paying attention to it. So if I'm going to collaborate with someone on the other side, I've got to collaborate and I've got to be with them to the end. So I can't just take a whole genome prediction from someone else and use it without understanding it and then educating them on what I need in return. And so that's the greatest lesson I've learned. So appreciate it. I think I've got plenty of time for questions. I went pretty quick. So thanks again.
Are there any questions for Dr. Kuhlman in the room or on the webinar? Behind you.
On your historical yield gain model that you showed there, did you look at it from 1994 onwards? I mean,
I won't go back through it. I haven't. Others have. Others have. You know, it changes. So you can break that data set up into lots and lots and lots of small chunks, and you can get flat regressions through periods of time that are not related to the Ranapredy 1 integration. But yeah, you can break up into lots of different pieces.
Are you generally moving to higher maturity in your area?
The question is about are we going to later maturities? No, maturities stay essentially static in the Midwest. In the South, the Delta regions, and further south, there's a break point at about maturity group 5 that's determinate versus indeterminate, so the flowering types. Traditionally, determinants are 5.0 and greater. Indeterminants are 4.9 and below. So the flowering patterns of corn is determinate, so it flowers in 10 days. So indeterminate soybeans flower over about 6 weeks. Indeterminate soybeans have usually a much more robust tolerance to heat and drought because they can flower over a longer period of time. So actually the maturity shifts that we see are in the Delta and South moving to earlier maturities because they're actually seeing higher yields in the indeterminate germplasm. So they're moving away from determinate varieties.
Les, a great presentation. Thank you. We are always talking to students. We enjoy the successful stories, and then we leave these headaches for industry to solve themselves, right? Yeah. And then there's 2 points actually connected. One is that the prediction accuracy within the elite material seems to be lower, somewhat expected, right? I mean, that as we narrow down the genetic diversity or genetic variance, and unless we have high throughput phenotyping like Michael Gore is doing to reduce our sigma square E by default, just the heritability calculation of sigma square E over sigma square G plus E, leaving the G by E out, you were expecting that the prediction actually going to be low anyway because we're narrowing down to the specific range of materials to do prediction. You have to run like tons of trials to get this entry mean based heritability to be high, which will make this prediction more accurate, right? That's one comment we can discuss. And another interesting question about your diagram about talking with breeders, statistical genetics, and then the genomics. So I'm just thinking that you don't have to answer this question, but just try, right? When you establish the genomic prediction model across all overall maturity range, remember the Boomer's #1 rule that figure out the base population of the genotype and the environment. So the prediction equation we establish through the whole maturity groups. But then if you as a breeder try to narrow down to just looking at maturity 3 or that specific group, did you call your statistical geneticist, ask them to run another prediction model just using that specific subgroup? If you use that subgroups, you would wonder whether you have enough original data points to allow that have to be higher. Right. Anyway, yeah.
Definitely. Once that's a negative example that's shown. The follow-up emails and questions are very different about how we can make this better and how we've maybe missed the mark. But I think one of my points of this presentation was that's the conversation has to be done. So if you're a statistical geneticist, you have just as much responsibility to figure out what the breeder needs as the breeder does in telling you. You know, it's that learning that has to happen. Yes, when you take that, you know, group 00 to 7 and take just a training set that's 3.6 to 4.9, the total variance is lower, but the variance that's correlated to your prediction set is higher. So the proportion of variance that's actually correlated to your target prediction set is a lot higher. So you actually get better. You get better predictions. Yeah.
You say maturity is correlated with yield. What do you mean by that? Like earlier the plant mature, lower the yield, or?
Yeah. So if you're in an environment and you have a segregating population, the longer the maturity, the higher the yield, because it has more growing degree days in which to produce yield, essentially.
Okay. Actually, I work on cowpea, but I have seen like the earlier maturing and very late maturing plants tend to have lower yield. So that's good. Thank you.
But probably not yield, I think.
You ask it, yeah.
I think, in my opinion, the later the maturity, it improves probably quality. I think I must have heard from somebody who said the later maturity cotton actually has better quality. But yield-wise, I think later maturity and increase in yield probably may not be that accurate. I mean, to correlate and all.
In maturity and yield are correlated in quite a few crops. When I mean, even in corn, CRM.
When you said later maturity also increases the yield, is it really true? Just I don't know much, but
in soybeans it is. Yeah.
Les, this isn't a scientific question. It's more of a question for the students, I think. So you did all of your training in sorghum, and then you were hired by DuPont to start a soybean breeding program. And, you know, you always hear, oh, if you can breed one crop, you can breed another one. But what did you face as a brand new Ph.D. graduate going to a company where you had to produce value pretty fast, I'm assuming, when you moved to a totally new crop and you were starting that program from the ground up?
That's a good question. I don't know if I knew what I was getting into, and I don't know if they knew what they were getting when they hired me. There's one really good thing when you move from being a PhD into a brand new crop. One is it lights a fire under your feet, which is you know nothing. And so it is your job to figure out as fast as you can, you know, what you're doing. So, you know, there's really no room for error there, I guess. Not that there's no room for error, but there's no room for sitting around and just, you know, you need to know quick. And so it was definitely time to learn quickly. The other huge benefit is it causes you to question absolutely everything. So, you know, I say, well, you know, why do you run your program like that, you know, other breeders? And they give me an answer. I can still claim ignorance and say, that doesn't sound right. That seems pretty dumb. Like, why don't we do it this way? And so you get to question every single step. And I think the benefit to the company is actually diversity of perspectives. So we run breeding programs quite a bit different now than we did when I started, not only because of my presence, but just the fact that we're able to question a lot of pieces along the way allows you to think differently. So that's a big positive. And I think, you know, I think Pioneer does a pretty good job of having a little bit longer term look. You know, if you hire somebody expecting results in a couple of years, you know, I don't know if that's probably the right hiring decision. If you've got a little bit longer term view of it, you know, the right graduate students, you know, you can tell. I mean, they've got drive, they're fired up, they're ready to go. You know they're going to show up and bring their A game to your company. You don't really have a worry that it's going to take them a year and a half to get going, because you know once they do get going, you're going to get paid off.
Thank you. You had a slide comparing your program private versus public, I guess.
Okay.
And then you had a line there that was that you were resourced to win. Do you think how significant that is comparing the two systems?
Public, private?
Private versus public.
Yeah. I don't know. I don't have enough public experience. I think it's an advantage, obviously. I think it is a really important 100% of my time can be devoted to adding value. That's what I'm asked to do, is create value for the company. And if I have to worry too much about not being able to pay my staff, or having to let people go, or not having the right equipment to do my job, it just ends up hurting the company because I'm not able to do what I need to do. So being a resource to win is a huge advantage, because you just don't have, that's one less thing that you have to worry about. You can focus more on the science and actually creating that value. It's not free from challenges, though.
So if in the public system, we equip our breeders with the resources to win, we can be as competitive as DuPont.
Yes.
Interesting.
Are there any more questions? There's one more.
You're in an area where there's a lot of wheat,
Yes.
and occasionally soybeans are planted after wheat.
Mm-hmm.
Do you have any special programs for double crop soybeans?
Special programs is in
In terms
technology.
of breeding, yeah.
We do. That's a timely question, actually. We do. So DuPont has the original STS gene, a mutant that's tolerant to STS or sulfonylurea herbicides. We actually have a new technology called BOLT, which is 2 of those genes. So it actually allows for much higher rates of SU tolerance in those soybeans. So it allows double crop. You can have a lot higher rates in wheat and then plant soybeans afterwards. So both of those things allow for the double crop soy after wheat rotation to occur. Mm-hmm.
You've mentioned several times that you're breeding for a value, but it take 8 to 10 years for you to develop a new variety.
Mm-hmm.
So what do you use personally as your crystal ball to predict where the market value will be in 8 years?
Yeah. Well, it starts with knowing your environment. So what's important to your customers. So for my breeding program, I've got a list of 5. Those 5: yield, number 1. SDS, tolerance to sudden death syndrome. It's really important to my customers. Everything we produce is soybean system nematode resistant, and then charcoal rot and drought. So those are my game. That's my game day. Is those. A different breeding program is going to have a different 5. So those aren't as shifty, if you will. Drought is always going to be a big deal in Kansas. So I can invest in that type of research, knowing that that's an 8-year play that's fine. The harder ones to deal with are technology changes. So, okay, what herbicide package do our customers are going to be wanting to buy in 8 years? That's a trickier one. So that requires the crystal ball. You get it when you start.
You mentioned the highest yield in your graph was 40 bushels per acre. 40 bushels per acre, but there was a farmer here who came sometimes and he said he got 10 tons, almost like.
Oh, that was national averages.
Yeah. So what's the maximum yield that has been obtained in soybean in your program, or what's the potential?
154 bushels the acre is the current world record holder.
That's almost like maize, like.
Well,
corn, yeah.
maize is what, 400 now, right?
Oh.
Yeah. But yeah, 154 bushels, farmer in southern Missouri. So
that brings my follow-up question on the, this has been almost through conventional breeding by evaluating both corn and soybean in high density evaluation. And rest all the traits follow. If you just plant them, their population in high density, select for yield, that's what has happened both in corn. So where would be the genomic selections taking this 150 bushels up? I mean, that's your experience. Thank you.
Prediction accuracy would be 0. I can tell you that from experience on that one. Those environments are not conducive to research. So they're fantastic for producing really, really high yields, but the amount of, so as you get in soybeans, when you get incredibly high yields, you also have incredibly high variances for disease traits that you didn't think existed. Everything is just magnified. So the amount of error in those 150 bushel tests are incredibly high compared to your normal production environments of 60 and 70 bushels. So the results we get from those types of trials actually aren't very applicable to breeding, we've found. In corn it may be totally different, but in soybeans the dynamics, when you get into those high yield ranges, it's just really not predictive of normal results.
I would like to make a comment on the early and late maturing stuff, the yield potential. If in the same segregating population with the same plant density or row spacing, yes, early maturing will be less yielding compared to medium and late. But if you take early maturing lines and plant in density, higher density, it will be almost as much as anything else. So, and I'm telling it from my experience in cowpea, we have got 60-day cowpea versus 120-day cowpea, and it matures in 60 days, gets about 2 tons, which is almost like cereals and per day productivity. So early maturity, wherever it fits, high yield can be obtained by plant population management, like this. So a general statement that early maturing is poor yielding compared to the medium and late, yes, under one density.
Sure.
But by management, it can be made.
Yeah, no, I don't disagree. These are in breeding populations where all those are the same.
Okay, that's all the time we have for questions. Let's thank Dr. Kuhlman once again.